We are very honored to receive this award. We really want to thank the committee. Today we are going to present our paper about super resolution and then the smallest singular value of Fourier matrices. I'm going to present the introduction and Weilin will present the main result. What is the super resolution? In imaging, the classical definition of super resolution is the capability of resolving two closely spaced point sources. So for the two sources, if we receive the diffraction pattern with a fixed aperture, and then we actually see the point sources blurred, well, the intensity is represented by the point spread function. So in the super resolution regime, so we hope that we can resolve those 2 point sources. Without super resolution, then we get confused. We might only see 1 point source and we cannot resolve their locations. In imaging, Lord Rayleigh introduced the Rayleigh length, which is the distance between the center and the first zero of the point spread function. The Rayleigh length is regarded as the diffraction limit. Super resolution has been an important problem in imaging. The Nobel Prize in Chemistry in 2014 was awarded to 3 scientists for their contribution of super resolution technique in single molecule microscopy. So for us, we focus on the recovery of point-like objects, which is common in far field imaging. For example, in the radar imaging problem, the sensor is very far from the L plane. So the goal is to recover the location of the point sources of the L plane. And then, so in the simpler setting, we look at the direction of arrival in signal processing. Well, you put a series of sensors on the ground, and the goal is to estimate which direction the wave is coming from. So here we have 3 incoming waves. We want to estimate the angle where the wave is coming from. So this is an important problem in signal processing. In the mathematical setting, we can formulate the problem like this. Well, the unknown point sources is represented by an atomic measure mu, which is a superposition of a series of delta functions. Well, xj represents the location of the point sources, and aj is the amplitude of the point source. So importantly, we allow for complex amplitude. Okay, so if we put the sensors in the far field under some approximation in wave propagation, then the model can be written as follows. If we put capital M sensors, well, the little m sensor will measure the Fourier transform of the measure and the frequency m. So usually we have noise, so and each of the sensor, we have the noise eta m. The goal in this problem is to recover the location and the amplitude of the point sources from the far field sensors. Okay, so when we receive the Fourier measurement up to frequency capital M, okay, then we lost all the frequency beyond M. The Rayleigh length is 1 over M. It's a standard resolution limit. And the minimum separation between the 2 point sources determines the difficulty of the problem. Well, we represent by delta. An important quantity in this problem is the super resolution factor, which is the ratio between the Rayleigh length and the minimum separation. So super resolution factor measures how many point sources can we have in one Rayleigh length. Okay, so super resolution regime refers to the case where the minimum separation is much smaller than the resolution limit, and super resolution factor is bigger than 1. When we receive the Fourier measurements, the simplest method is to do the inverse Fourier transform, right? So if we do the inverse Fourier transform, then what we obtain is the original measure mu convolved with the Dirichlet kernel. Okay, well, the Dirichlet kernel is called the point spread function. And fortunately, when the point sources are well separated in the left figure, we can easily find these 3 point sources. But if 2 of them are closely spaced, then we get confused and only get 1 peak in the inverse Fourier transform. So you can see that the problem is difficult when the point sources get very close. So this imaging problem was also tackled from the compressive sensing perspective. In compressive sensing, people usually discretize the imaging domain to with a regular grid, and then approximate each of the point source by the nearest grid point. So in order to make sure that the approximation area is small, we have to use a very fine grid. Okay, after discretization, then the measure mu can be represented by a vector A of the same length of the grid point with the sparsity S. Well, S is number of point sources. Okay, so the support of the vector A is associated with the point source location. So in compressive sensing, if we take random rows of a DFT matrix, and we can recover the object accurately. And then, however, the super resolution setting says that we can only receive the frequency up to capital M. So actually, we only receive some low frequency Fourier transform, and we do not have any information beyond the capital M frequency. Okay, so compressive sensing tackles an interpolation problem, and super resolution is more difficult because it's an extrapolation problem. Okay, so even though it's very difficult, we still want to understand the fundamental limits and then also the performance of the good algorithm. We are very motivated by the pioneering paper by Donohoe in 1992. Well, the Minmax error is studied. And then in 2015, so the bound is sharper in dominant paper. And a series of work look at the recovery of point sources while they are well separated. So for example, the point sources are separated by a constant times the resolution limit. So this series of work is more like dealing the discretization error, okay? And then in 2016, so super resolution is addressed with TV minimization. Well, the point sources have a positive magnitude or the magnitude have a certain pattern, okay? So we want to look at the general case where we have complex magnitude. And next is our main result. I will pass to Weilin.
Okay. All right, so when we started this project, we kind of wanted to look at it from kind of like a sparse recovery point of view. So let's forget about any discretization error for now. Let's just suppose that the measure is actually on a grid. This grid has width 1 over n. So in this setting, it can basically be transformed into a sparse recovery problem, because if you have this S atomic mu, you can identify with this S sparse vector in Cn. And then the Fourier coefficients are just the sensing matrix F sub m that Wenjing showed earlier times the sparse vector U. So you're in the setting where you'd like to try to recover the sparse vector from linear measurements plus some noise, typical sparse recovery problem. So this is kind of now one of the main differences between super resolution and compressed sensing. If we study this min-max error, we want to study the performance of any given algorithm. So what is an algorithm? It just takes data and it produces an estimate. So if phi is like a function or an algorithm, it takes data of this form. This is our model. And then we measure accuracy in terms of the L2 norm. So of course, we take the sup over all perturbations of size delta, and then we have some normalization on kind of the signals here. And so this is like the max error here. And if we take the infimum over all possible functions, this is what's referred to as the min-max error, okay? And this is a very strong lower bound for any algorithm. This is the error incurred by the best possible algorithm with infinite computational resources. So no algorithm can perform better than this min-max rates with respect to this error function. So our first contribution with regards to this is a sharp estimate for the min-max error. So under certain conditions, we show that this quantity is on the order of this really important super resolution factor to the power 2s minus 1 times delta, where delta is the noise level. So this is a negative result, because if you imagine S being as like 10, which isn't unreasonable in imaging, like 10 objects, and you try to do high resolution imaging, so super resolution factor is kind of large, then in order to get a reasonable result here, the noise level has to be extremely small. It has to be inversely proportional to this huge number here, okay? And this is for the min-max error, which lower bounds any possible algorithm. So when we look at a result like this, it kind of says that, hey, maybe super resolution is impossible, but we're going to argue otherwise. And our line of reasoning is as follows. Basically, this error is attained by very special configurations of the sparse vector. You can imagine if all S spikes are consecutive and they have some kind of sign pattern, this is the type of signal that's hardest to resolve. But in practice, you might not encounter something as difficult as this. It might be better. So, so kind of back to the drawing board on this. Let's go back to the continuous model here. So we ended up studying these Vandermonde matrices with nodes on the unit complex circle, which we'll just call Fourier matrices. So you can see that these are generalizations of the usual DFT matrix. It's m+1 rows, S columns. So the support of the measure is arbitrary. These specify the nodes. And then if we look at the measure here with amplitudes A, then we can write the Fourier coefficients of this measure as this unknown matrix. This matrix is unknown to us because we don't know the support of the measure, times this unknown amplitude vector A here. And this, if we try to recover the measure from these measurements, it's a non-convex, nonlinear inverse problem. Okay. So we're going to make a bit of a jump here, and we're going to study the smallest singular value of these matrices. You might ask, why is this natural to do so? There's a few hints already. If you look at the Oracle reconstruction error, if somebody hands you the support for free, then to estimate the amplitudes, you just compute the pseudo inverse. So this is already one instance where the conditioning of these matrices appear. But also in the proof of the min-max error theorem that we just showed earlier, we actually have to go through these Fourier matrices as like an intermediate step, okay? And that's not obvious. And the third thing is they actually control the robustness of these subspace methods, which we'll return to later, and again, not obvious. So these things are classical. What can you say about these matrices? Well, going back to, say, Valor, it's shown that when the spikes are well separated enough, these matrices are essentially as well conditioned as they possibly can be, because they have S columns. Each column has L2 norm square root of M. And this result by Valor shows that the smallest singular value is on the order of square root of M. But once we go into the super resolution regime, the regime we care about the most, these matrices could be ill-conditioned, and there's not a lot of great results for this prior to our work. And this is because many classical works treat general configurations, which tend to be quite different from the nodes on the circle case. And moreover, we're always dealing with these very tall matrices, which behave quite differently from square matrices that were studied before. So what can we say about these matrices in the super resolution regime? We introduced this clumps model. So a set X consists of clumps if it can be written as a union of subsets, where each subset is what we refer to as a clump. And each one of these guys has to be contained in an interval of length 1/m, as you can see in this picture here. And this set will be described by two parameters, alpha and beta. Alpha will control the separation between the support set. So here alpha is inversely proportional to the super resolution factor. And the beta controls the distances between the clumps, okay? So you can think of this as a two-scale model. It's natural to really study this because it it encapsulates two extreme cases that have been studied before. The case where there's K equals S clumps, and then each clump just has a single point. This is the well-separated case. And then there's the worst case, which is what appears in kind of like the min-max error, where you just have one clump containing all S points. So it's kind of like something in between, but it captures both extreme cases. So our main theorem for this is as follows. So the main thrust of the theorem is that the alpha is arbitrary. Alpha controls the spacing between the points. It can be arbitrarily small. And beta here has to be sufficiently large. So beta controls the separation between the clumps. And we were able to show that there exists explicit constants, formulas are in the paper, such that we have this lower bound for the smallest singular value of this Fourier matrix. We have this square root of m, which is the natural scaling factor here. And then it's like an inverse L2 sum. Each term, really the main feature of this is that each term involves a super resolution factor, but the exponent only depends on lambda k. Lambda k is the cardinality of the kth clump. So just to simplify this a bit, you can estimate this in terms of the largest clump size. And this estimate, again, features a super resolution factor to a power that only depends on the largest clump. So you can think of lambda as like a local sparsity, if you want to. And this provides the following phase transition. Basically, when the super resolution factor is less than 1, you're in the well-separated case. These matrices are well-conditioned. But in the super resolution regime, the conditioning or the smallest singular value really depends on the geometry or configuration. As you can see in this exponent lambda, as you let super resolution factor grows, this thing will go to 0 at a rate that is highly dependent on the lambda. Okay, so maybe in the interest of time, I will skip the proof technique. I will just say that we relate this to like an over-parameterized min-norm interpolation problem, and then we do a constructive approximation. And this is how we end up with explicit constants for everything. Okay, finally, I want to now explain how this relates to subspace methods. So because this is just a 25-minute talk, we won't get into the details on the mechanisms behind any of these algorithms, but I just want to describe them at a fairly high level. So music and esprit are examples of these subspace methods invented in the 80s, primarily by engineers. There's very well-known algorithms. There's tons and tons of papers written on these guys. We're going to treat this from a more mathematical point of view. So music is essentially like a stabilized root finding algorithm. In the noiseless case, one produces this function R, and the zeros of R are precisely the support of the measure. In the noise case, you're unable to access R, but you are able to access a perturbation of it. So in this figure here, the exact R is in red, and the perturbed one is in blue. And if you find the local minima of the perturbed function, that will be the estimate of the support. So if we want to understand the stability of music to noise, then we want to examine the perturbation of R. So we are able to obtain this L infinity perturbation bound. So R tilde is the noise case, R is the clean function. And in the L infinity norm, it's like this. So again, you have the noise level, you have a bunch of other things, but the important part here is the smallest singular value of these Fourier matrices that appear again. And so under the Clumps assumption, we can write this in terms of the super resolution factor. So we end up with this guy here. And you can think of this thing as the numerical conditioning of this algorithm. And importantly, the numerical conditioning only depends on super resolution factor to the power lambda, as opposed to S. And lambda can be much smaller than S. So we have some simulations that agree with our theory. Basically, our theory says that as we increase the super resolution factor and increase the noise, the harder the problem becomes. As we increase the lambda, the harder the problem becomes. These are phase transition curves, so they tell you the region of parameters where you are kind of where this algorithm is successful. And as we increase lambda, the regions shrink, which is expected. But more importantly, if you compare these two figures, they're very similar to each other. And that's precisely the point, because our theory says that it's really the super resolution factor as well as the lambda that really controls stability. if we increase the number of clumps or increase the total sparsity, the number of point sources, it shouldn't affect the robustness or the stability of this algorithm whatsoever. Okay, and so for the conclusion.
Finally, I'm going to conclude our presentation. After our paper was released, and then there also have been many interesting works in this direction, such as the conditioning of the Fourier matrices that we'll study. And also superresolution was also studied from the Minmax error in the as a theoretical information theoretical limit. We also extend our work in several directions. With Professor Albert Wenjing, we look at the E-spread algorithm, which is a very well-known algorithm, very classical. So we proved that the E-spread will give us support error upper bounded by the super resolution factor to the 2 lambda minus 2 power. Well, lambda is this local sparsity times the noise level. And importantly, so we can compare this with the lower bound proved by Bantakov. Well, they show that if we have lambda equally spaced point sources, the support error has the lower bound as a super resolution factor to lambda minus 2. So our work proves that E-spread is an optimal algorithm because the upper bound matches the lower bound. And recently, we worked on the multiple snapshot regime. So in the previous setting, we assume the source amplitude is deterministic. And then in some of the applications, the source amplitude A can vary over time. And then we can take multiple snapshots of measurements at multiple time. We prove that E-spread has the error bound of super resolution factor lambda minus 1. Okay, so important, you can see that with the information in multiple times, so we really improve this factor, the conditioning, we reduce the power by a factor of 2. So which shows that the time information can be very helpful. Okay, and so finally, we summarize our work that we study super resolution with the sparsity information. We proved the min-max error, which is a little bit pessimistic when the sparsity is large. But what really matters is the local sparsity, how complex the point sources are in a local neighborhood. So we introduce the clump model, and then we improve the error to the super resolution factor of 2 lambda minus 1 minus 2. Well, lambda is the local sparsity. Okay, so we're utilizing the local geometric information is a significant improvement of using the sparsity only. Finally, we want to thank you for your attention and thank you the community.